So with this, I'm coming to the last part of my talk, which I'm going to show you our new understanding, or our understanding of silicon carbide substrate influence on top layer graphene. So let me first show you my first observation that's motivated me to consider the impact of the substrate on top layer graphene. So you already are familiar with these three samples, the morphology of these three samples, but I would like to draw your attention to SEM images of these three samples. So you can see in the bottom, in case of S5, you can see a kind of contrast pattern on these samples, which is attributed to the monolayer and bilayer inclusion. So you can see this more clear in the case of when you notice the AFM Raman spectroscopy of this sample. Nevertheless, it's very interesting when you see the epitaxial graphene sample on 6H and 4H samples. So again, you see a kind of contrast on neighboring terraces, despite the fact that we have pure monolayer graphene on both samples. So this motivated me to investigate further the influence of the bottom substrate on top layer graphene. Interestingly, the AFM image, the AFM inspection also shows the same effect. So here you see the graphene grown on two samples, 6H SiC substrates. So with different morphology, we can grow graphene with the advanced control, we can grow graphene on sequential steps and terraces with 0.25 and 0.5 nanometer, or simply 0.75 nanometer terraces. So from the Raman spectroscopy at the bottom, it verifies formation of graphene on both samples. Interestingly, the phase image of these two samples shows that when we have these sequential steps and terraces, we get some phase contrast on these two, on the neighboring terraces, which is not happening when we have 0.75 nanometer steps. This pointer is really narrow. Okay. This is the same scenario in case of a buffer layer. So again, two buffer layer samples on 6H SiC. The Raman spectroscopy shows formation of the buffer layer. And again, the phase image shows when we have steps of 0.25 and 0.5 nanometer, we see this contrast, which is not happening when we have 0.75 nanometer steps. From this AFM inspection, we already can conclude two very important implications. So first of all, this clearly shows that this is a substrate related effect. And second, we can really exclude an intrinsic effect between the graphene and buffer layer, because we see this effect also when we don't have the graphene. So what does this mean? We need now to identify the steps and terraces to be able to study their impact on top layer graphene. I'm going to show you these through so-called JCH model, joint cubic hexagonal model, which will be verified by different characterization methods. So the formation of steps and terraces can be understood during the growth, can be understood by applying or in the framework of a step retraction model. So here you can see the unit cell of silicon carbide, 6H SiC. The position of each atom has been shown as hexagon, or as H, as hexagon, or cubic as K. And you can see that that the bonding nature in on and off axis direction is not the same. For instance, you can see that in case of S2, we have K or cubic bonding in both on and off direction, which is not the case in S3 and S1. So S2 is 100% cubic, and S3 is like 66% cubic, while S1 is 33% cubic nature. So from the literature, we already know that the S1, the hexagonal layer vanishes first. So the S1 removes the first. So when the S1 is removed, S3 and S2 shape the surface below the graphene. From this, we can already extract two important rules. As you can see, S2, when S1 is removed, S2 is always above 0.5 nanometer steps. And S3 is always above 0.25 nanometer steps. So we can later use these rules to identify the steps and terraces. So if we now continue the growth, the S3 becomes narrower and S2 becomes wider. And if you finally give enough time, then you end up with S3 removes and S2 shape the surface. So now let's apply let's test the JCH model by using LEEM investigation, or low energy electron microscopy. Here you can see the lead image of the sample shows successful graphene formation on 6 SiC. So if you now consider the LEEM bright field image of this sample, you can see a kind of contrast again on reflectivity contrast on the neighboring terraces, which is very similar to AFM phase image and SEM images. Now if you notice the LEEM IV image, the spectroscopy of the images captured from these two areas, the magenta and green area, you can see that we have like one minima in the spectra of these two spots. So this is clear indication that we have monolayer graphene. So if we had two-layer graphene, then we got two minima. So again, we can now conclude clearly that this contrast that we see in the AFM phase image or LEEM bright field has nothing to do with the thickness variation. So we have pure monolayer graphene on both terraces. So now let's apply the JCH model. From the JCH model, we have the following information. S1 is removed, and S2 and S3 shape the surface. So from this terrace width and the analogy between the AFM images, we can now visualize the steps and terraces on the surface on this LEEM image, as has been shown here in this blue line. So based on that, we can now map the surface, like solving a beautiful natural puzzle. Good. So now we can further test the JCH model using LEEM dark field. So the LEEM dark field is recorded by the Mori diffraction spot. This arises from the multiple interaction between the graphene and silicon carbide substrate, which gives us information about the substrate below the graphene. So here you see the LEEM dark field image of the same sample. Again, you see a kind of contrast, or binary contrast, which arises from the 60-degree crystal rotation, as can be seen from these macro-lit images of the sample. Now let's compare this lead bright field and lead dark field. So you see that the contrast here, the frequency of this contrast is different than the LEEM bright field. If you have a closer look, you can see in the regular steps pattern of 0.25 and 0.5 nanometer, each contrast in LEEM dark field comprises of two contrasts in the LEEM bright field. In other words, we have the S3 and S2 or SN have the same color contrast in LEEM dark field, and the contrast changes when we go to the SN, a star termination, so S3 star or S2 star combination. So you can see this constant, that the contrast, the difference between these two types of contrast. This could be more clear. Accordingly, we can now map the LEEM dark field as well. This consistency can be better seen in this image. As I made this sketch on the left side. So again, each contrast in the LEEM dark field comprises of two terraces on the LEEM bright field, S2 and S2. For instance, S2 and S2 star and S3 star have the same color contrast because the crystal below the graphene have the same direction. So using JCH model, you can also map the surface when you have irregular terrace on the steps, as has been shown with this in this blue line here, or the red one that has been shown in this image. So this is very important. So based on this JCH model, we can now map even the complex irregular steps and terraces. So this shows that with this, I showed you that the JCH model we can map with the JCH model we can map the surface, identify the steps and terraces below the graphene, and has been verified by using several characterization methods. So. So far, we can, little summary again. So far I showed you that we can have the graphene, a buffer layer, or graphene on identical or non-identical surface terminations. And now we can successfully assign or identify the steps and terraces below the graphene. And the next, I'm going to show you how we can quantify the influence of these layers on top layer graphene. So the first technique is KPFM, Kelvin probe force microscopy, which is a very versatile technique that we can get information about the surface potential difference and work function of the samples. Here on the top you can see the AFM topography of the sample. From the profile of the steps and terraces, we can now identify the steps and terraces, like the termination has been mapped in the image here. In this image, you can see the surface potential of the sample of the same area. These red-like area are attributed to bilayer graphene, and so you can see the surface potential increases when we have bilayer information. But beside the bilayer inclusion, which is happening at some defects on the surface, we have also this contrast, surface potential contrast on the neighboring terraces. So from the graph made here, from these two lines, the magenta line and green line, you can see that we have like almost 10 millivolt surface potential difference from between S2 and S3 terminations. Here you can see the closer look in this area from the map of these rectangular areas made in this histogram. You can see again a kind of like 10 millivolt, 10 to 12 millivolt surface potential difference or work function difference. So this is a clear signature that we have the work function is different on these two terraces, and technically, accordingly, the doping is different. I have to add that this KPFM measurement was performed in air. So you should expect the influence of the air in the measurement at low resolution. As a second method, we used low energy electron reflectivity, or LEEM, IV-LEEM. So I already showed you the spectra of these two samples. As you can see, we have one minima, so clear one layer. But if you have a closer look on this area, you can see that the minima happens or occur at two different energies. So this is the map of each single pixel from the LEEM bright field at a low at the minima. So you can see clearly that the surface energy are different at these two different areas. So from the spectra made from this rectangle area, you can see that the graphene energy at these two, at S3 and S2 are different, and this energy difference is almost 60 milli-electron volt. So this measurement was performed in vacuum, and we expected to have to see better measurement. Good. As the third complementary technique, we use X-ray photoemission electron microscopy, XPEEM. So this is a very interesting measurement. So with XPEEM, we can directly measure the work function on the surface. So if you see any contrast in the XPEEM images, it directly shows you it can visualize the work function variation on the surface. XPEEM also enables to have simultaneously the LEEM investigation. So here you see the LEEM bright field image shows the same results or confirm the previous results. So it shows that the results are not just accident or incident. This is like a universal effect. So from the XPEEM image captured at the same area, we can see that there is a contrast, work function contrast on these two neighboring terraces belonging to S3 and S2. So the darker area has higher work function compared to the brighter area. So this supports the measurement by KPFM as well as LEEM bright field or IV-LEEM, and give us clear indication or unambiguously shows that we have work function variation on S3 terminations. Good. So with this, we come to the question, what is the origin of this effect? So we already showed that we have doping variation on these two type of terraces, but how we can explain this effect? So we already know that hexagonal silicon carbide shows a kind of a so-called spontaneous polarization, and this spontaneous polarization leads to a kind of a so-called polarization doping in epitaxial graphene. There are two very interesting, valuable papers from Rieshlein and Samir Mamadov. I think Samir is also joining us today. So this works technically like a progress of what they have done. So they very well explain what's happening and why we have a kind of p-doping in quasi freestanding graphene layers. They also showed in their model why we have n-type doping of epitaxial graphene. So the polarization doping is the main responsible for the p-doping in quasi freestanding graphene. And in case of epitaxial graphene, we have an overcompensation of donor-like states from the buffer layer, which leads to have n-type doping in epitaxial graphene. This model, however, consider a homogeneous doping on whole terminations. So, but the results that I showed you with different characterization, we can see that the doping is not similar or homogeneous on all terminations. So with this, we clearly can see that the stacking order is the main reason to have the different doping on silicon carbide on epitaxial graphene. This is in a very well agreement with the theoretical expectation or calculations done by different scientists already from 90s. And more interestingly, the recent work from Davood Momeni Pakdehi. So they expected with their calculation that the doping should be different on different terminations. So luckily, Davood is willing to do some more calculations on such graphene samples. So now let's take a second and see what does this mean. We have been able now to grow graphene or fabricate graphene on silicon carbide with non-identical terminations, which the doping is different. So this all is happening based on the properties of silicon carbide, the stacking order of silicon carbide. So this, I believe that this opens a new door for kind of growth-mediated doping engineering in silicon carbide. Yeah, and I pretty expect that the same effect to be seen in similar material systems. So with this, I'm coming to the end of my talk. Let me wrap it up so far, the highlights. So I showed you the first time that the argon gas flow can change the surface properties. We can control the growth by using the argon gas flow. We reach the minimum resistance anisotropy in epitaxial graphene, which is very important. We can enhance the electronic properties of the devices made out of this. I showed you we can get large area buffer layer formation, and we can turn it to quasi-freestanding graphene samples, homogeneous and large area. And we can have an advanced growth control. We can grow the graphene on identical or non-identical terminations. And I showed you the first experimental results of the silicon carbide surface-dependent polarization doping. And so the processes are very reproducible. Now we had a numerous number of samples that we got a very good quality of the samples. And I showed you using this JCH model or joint cubic hexagonal model, we can model or identify the steps and terraces, which was verified using different characterization techniques. And this gives us an insight into our complex material system, the difference of the polytypes, and also help us a lot to for the realization of the flat graphene for quantum resistance metrology. So I'm coming to the end, but it's very important. I want to thank all my colleagues at the PTB and the groups that I've been collaborating with them, from Uni Hannover, Uni Chemnitz, group of Professor Zeiler, Philipp Florian, also group of Professor Teinkam, Johannes Nyung, and also from the Göttingen, Martin Wendrud and his group, Anna, Philip, and George, as well as Uni Braunschweig, Professor Barking. Special thanks to Alexei from Lund, and also thanks a lot to the support from the GIGS project, and thank you for your attention.